So we're going to be moving on to the topic of magnetic fields. And the best place to start is by looking at the field lines of something simple like a bar magnet. So we have a simple bar magnet, and here's what the magnetic field lines would look like. So here's what the field lines look like, and you can notice that the field lines always point from the North Pole to the South Pole. Now you may also notice that the spacing between these lines differs. You can see that the lines are much closer at the centers or towards the poles. And when you have closer field lines, this means that the magnetic field is in fact stronger. So in the case of a bar magnet, you'll see that the magnetic field is strongest at the poles. And here's what the field line looks when you bring two magnets close to each other. And the field lines look like this as the two north poles repel each other. Now one thing you need to make sure is that your field lines don't cross over each other. And I know in this case I haven't drawn it properly, but in your exam just remember that. Now let's look at some relationships between currents and magnetic fields. Whenever a wire carries a current, it will induce its own magnetic field. So if I had a wire with the current flowing this way, this wire would induce its own magnetic field. And the direction in which this magnetic field is produced is governed by the right hand thumb rule. And what this is if you point your thumb in the direction of the current flowing, your forefingers will tell you in which direction the magnetic field is going. So in this case, if you were to point your thumb upwards, you can see that the magnetic field would flow anti-clockwise. And if the current was actually flowing downwards, you would see that the magnetic field flows clockwise. So let's say I have a permanent magnet, and a permanent magnet means something that will always have a magnetic field. And as we know, the magnetic field lines flow from the north to the south. Now if I now insert a wire, and I say that the current is flowing upwards, well, we know that this wire is going to produce a magnetic field. And again, this magnetic field will be in this anti-clockwise direction. And we can get this via the right-hand thumb rule. So the wire carrying the current will induce its own magnetic field. And what this means is this will interact with the permanent magnet's magnetic field. So there's two magnetic fields, one from the permanent magnet that we can see going from north to south, and the other one which is induced by the current flowing through the wire. They will both interact with each other. And therefore, there will be a force exerted on the wire. And how can you determine the direction of this force? Well, you have to use something called Fleming's left hand rule. Now excuse this awful drawing, but if you get your hand into a sort of gun shape, where your thumb, index and middle finger are all pointing in 90-degree angles, well, here your thumb is going to be representing the force on the wire, your index finger is going to be representing the magnetic field, and your middle finger is going to be representing the current. The symbol for force is your letter F, the symbol for magnetic field is a letter B, and the symbol for current is your letter I, so you can just imagine this as some sort of FBI sort of symbol. And you want to keep your hand in this shape and rotate your hand such that your fingers point in the directions of the force, the current, or the magnetic field. So now in this scenario, we know that the current is acting in the opposite direction, and the magnetic field is acting towards the right. So if you were to use your Fleming's left-hand rule, you will find out that the force goes into the page. And here are some symbols to represent whether something is coming into the page or out of the page. As you know, it's easy to depict if something's going up, down, left or right using arrows, but in the case of going into the page or out of the page, you need to use one of these two symbols. All these will be given to you on your paper. So for the symbol for coming out of the page is a dot, and the symbol for going into the page is a cross. And the way to remember this is by thinking of this as an arrow or a dart. If you were to shoot a dart or shoot an arrow, you're going to end up seeing the cross, as that dart or arrow is going away from you. But if that dart or the arrow is coming towards you, you're going to be only able to see the end point, which looks like a dot. So if you're unsure what the sign means, Just think of an arrow or a dart. So we've now calculated the force on a current carrying wire when it's present in a permanent magnet's magnetic field. So now let's look at the equation, which will help us work out the size or magnitude of that force. And the equation is F is equal to BIL sine theta. F here is your force acting on the wire in newtons. B is the magnetic field strength, or sometimes it's called the magnetic flux density, and is given in the unit of Tesla. I is your current in amps, and L is the length of the wire in meters. And theta is the angle between the wire and the magnetic field lines. So if this was your wire in some magnetic field lines, this would be your angle theta. So we've looked at the force on a current carrying wire. Now let's look at the force acting on charged particles. So let's say we have an electron going into this region here where there is a magnetic field. And remember that this sign means that the magnetic field is acting into the page. And this electron is going to be moving in there with a velocity v. So due to the moving charge, there will be an induced magnetic field around the charged particle. And this induced magnetic field, just like in the previous case, will interact with the magnet's magnetic field. And therefore, there will be a force on the charged particle. And you can use your left-hand Fleming rules again to work out the force on this charged particle. Well, we know the B field is acting into the page, and we know that this electron is moving towards the right. But because an electron is a negative charge, the current will be actually flowing in the opposite direction. So if you use your FBI rule, you point your B into the page, and you point your current towards the left. So you can see that as this electron, as it's going towards the right, the force is acting downwards. Now obviously if this was a positive particle, the current will be flowing in the same direction that the charge is moving. So if this was a positive particle, the force would be upwards. And you can see that here that the force is perpendicular to the velocity. So what you will actually get is circular motion. Charged particles exhibit circular motion in B fields. And what I mean by B field is a magnetic field. So if you have a magnetic field present, the charge will undergo circular motion. And you know from our old equation, F is equal to BIL, and I is your charge over time. And what you can do is factor out this L over T here, and we know that this L over T is like a distance over time, and therefore this is a velocity. So you can say that your magnetic force is equal to BQV for charged particles. And since we know it's traveling in circular motion, this magnetic force is equal to our centripetal force. So you can say that BQV is equal to mv squared over r. So as your charge is moving in the circle, we can find out that the radius of this circle is equal to mv over bq. And you don't necessarily need to remember this equation because it's quite simple to derive, but it's an equation that you will probably be asked to know for your exam. Now the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.